screen and let you take it from here.
Thank you, Dave. Hi, everyone. My name is George Zoto. I'm a data scientist at a nonprofit in DC called Share Strength. I'm also the co-founder, co-organizer of another cool community called Deep Learning Adventures, as you've heard Ted and Ryan mention us before. And today we'll be talking about chapter 12 of our Aurélien Géron's machine learning book. Just a warning, this session will be a little bit code heavy. So if you want to grab your cup of coffee or tea or whatever, a cup of water, I'll try my best to keep us engaged. But again, there's so much limit as how much information one can absorb looking at code. So I'll try my best to make it as interactive as possible. But then again, the nature of this chapter is very code heavy compared to others. Cool. With that said, let me share my screen. So this is the book that we're going over for all of you joining us on YouTube as well. We've covered 11, 12, 10 chapters by now. And this is the type of this chapter 12 that I'm covering today. This is an excellent resource. It's also paired up by a GitHub resource that you can experiment with different modules as you're learning TensorFlow. And Aurélien also has some other resources that he explains different concepts. So I don't have a lot of slides. I just included the main visuals that I think are important for this chapter. And I'll actually go over a modified version of Aurélien Géron's notebook for us. And a couple of slides is just taking a step back. So far, we've seen the traditional machine learning approach, as well as we took our first deep dive, or not deep dive, but 10,000 level view of how to develop a deep learning model. This chapter actually zooms out a little bit and exposes us to new concepts, and especially what is called the TensorFlow ecosystem. So that is comprised of different products, APIs, and solutions for us to basically divide our data science projects into pipelines. So there's a way for us to load and pre-process data. There's a way for us to build and train models. There's a way for us to deploy them. There's a way for us to deploy them on different devices. And on our Deep Learning Adventures community, we've deployed them on the browser using TensorFlow.js, on mobile devices, on TF Lite. And the next step would be to deploy it on cloud servers, on heavy compute cloud servers using TensorFlow Extended. We've seen a little bit TensorBoard last time, and a way to look at your logs and visualize your performance of your model. So that was an interesting tool. And we're not going to look today at TFX. I don't know if the book even covers, I think it does in the very end, but that's a way to productionize your machine learning pipeline and deploy it on the cloud. So by now we've heard about TensorFlow, but just to summarize a little bit what it is and what it isn't. So it's a powerful library for numerical computation. It's really well suited for large-scale machine learning projects. It initiated at Google Brain as an internal product from Google, and it actually supports even now multiple products, including photos, search, and other internal and external Google products. It is very similar to NumPy. You'll see a lot of NumPy-like syntax and operations, but don't get distracted by that. There's a difference in the end. It just has way more capability and features. It supports GPU. It supports distributed computing. And its own just-in-time compiler that optimizes your code based on which node of your graph is executed, as well as where the code is running on what machine. Another cool thing is you can develop a deep learning model or a TensorFlow model in one setup, for example, in Linux and Python, but then you can convert it and run it on a completely different environment, like, for example, Android device using Java. To me, that's really interesting, because makes your code portable, and also you can run it on multiple devices and build all kinds of cool applications. We'll also talk a little bit about the AutoDiff, the automatic differentiation library that TensorFlow uses under the hood to compute the gradients and propagate them into your network. Any questions about this so far? Feel free to ask or chat. Cool. Then being a little bit more concrete about this high-level API, the book mentions the two ones, tf.keras and tf.estimator. And just to clarify, anything that begins with tf, TensorFlow, that's TensorFlow implementation of Keras. So there's a Keras implementation on its own. You're welcome to use it, but as of TF TensorFlow 2, Keras is actually implemented within a TensorFlow environment. So anything that begins with tf.keras is TensorFlow version of a Keras implementation. Just to keep that in mind. We're not going to see estimator, and actually, I think that's being eclipsed now. I haven't seen a lot of applications using tf.estimator as a high-level API. We'll definitely see today maybe metrics optimizers and initializers. We might have seen them, I think, in the previous chapter as well. But this is how we look at lower level APIs for different metrics and optimizers. We'll look at gradient tape and gradients today and AutoDiff and what does that mean. And in another chapter, we'll look at how do we do input, output, and pre-processing. So how do we do structured data? How do we deal with images, with audio, with cues, and so forth. We've seen a TF summary in the past, a way for us to summarize our network visually, as well as its integration with TensorBoard. There are other APIs here that we won't get the chance to cover, but there's APIs for distributed deployment and optimization for special data structures like sets or sparse tensors, as well as linear algebra and signal processing. So that's the high-level APIs. And there's way more, and there's links on the next slide where, as also on the book, where you can look at all of them. Again, keeping a high-level overview. Let's say we're using Python code. You can actually develop this in other languages as well, like C++, Go, Java, and Swift, I think. But in the end, what does the architecture look like? So we have our Python code as our very high level. For most of our projects, and this is what we've seen so far, we'll directly interact with either the tf.keras API or tf.data API. There will be circumstances, and that's what we're going to cover today, where we actually need to go a little bit lower and talk about how do we customize things, how do we make them fit our specific project needs. And then the TensorFlow architecture itself has a way to distribute it based on, if this is a local machine, it will just run on your local CPU or GPU. But if you have a cluster of machines, it will optimize it and distribute it and execute it on a distributed cluster based on your availability of CPUs, GPUs, or tensor processing units, TPUs. Just a couple of slides. We're going to look at this later, but this is just a preview of what things we can do with customization. We can build custom models, custom layers, custom weights, initialization, custom metrics, custom loss functions, as well as in the end, we're going to look at these graph operations that happen when TensorFlow gets compiled. I included here a list of resources that I came across during this chapter. The first one is the notebook that Aurélien covers. One is the edited version of it, and the rest are different resources that are either mentioned directly in the book or I came across while looking up things on my own. Specifically, the last two are related to tracing and autograph, which I think need a little bit more coverage in my opinion. Cool. With that said, those are the only slides. I'm gonna take a pause here before I switch to the notebook and see if you have any questions. I'll pause here for a second.
Hey, George, just one quick comment. I noticed in the book, Aurélien says at the time of the book's printing, he recommended that people use standalone Keras because tf.keras was still at that time relatively new, might have had some bugs. I think at this point, the conventional wisdom is the opposite, is you're better off using tf.keras because it's going to be the same version as your TensorFlow. And if you use regular Keras, it's possible that you could have a slightly different version of TensorFlow that's not necessarily exactly paired with the version of Keras that you have installed. And so you can get, unfortunately, potentially like some bizarre bugs that are just because of version differences that will be very, very difficult to trace. And unless there's just some brand new feature in Keras that for some reason isn't in tf.keras, you're better off just using tf.keras. Would you agree with that?
Yeah. I mean, for all our projects, we've only used tf.keras, but yeah, it used to be the case that Keras was a couple of minor versions ahead. I think the TF team is doing a hard work of keeping that implemented under the TensorFlow ecosystem. But yeah, usually when you build a project, you utilize either libraries, for example, IO libraries like tf.data. So it makes your life much easier to just be under the TensorFlow umbrella. Cool. If there are other questions, I'm going to switch gears to the notebook. I'm going to zoom in a little bit so it's easier for us to look at. But again, the point here is not for me to go through this very long notebook line by line, but rather just give us the high-level ideas that we came across in this chapter. So as a high-level summary, again, we mentioned that using just the tf.keras API, that will cover about 90-95% of the cases that we've seen, and that cover multiple scenarios, image processing, natural language processing, structured data, time series. But for that special case where you're going to need to modify maybe or develop your own loss function or your own custom metrics or your own layers or even your own models, for example, the wide and deep net that's mentioned here in this paper, or even your own regularizers, how you want to penalize highly high values of weights and so forth. So to do that, the book actually goes through an overview of how does TensorFlow work, what are its main data structures, data sets, how operations are defined, and how do you actually get to customize them. So we're going to start with importing a few libraries. The main ones that we're going to need is TensorFlow, and from TensorFlow, Keras. Going to need NumPy just for comparison reasons, as well as some visualization libraries here from Matplotlib. Scikit-Learn, I think we'll just use it for importing data sets and training and splitting training and validation sets. And System for saving the model on our local system and loading it again. Cool. So the first concept that we need to be familiar with is the concept of a tensor, which is basically the main data structure that TensorFlow offers. It is very similar to an ND array in NumPy. And the way you would define it is, for example, a constant tensor, you do tf.constant, and you pass either a constant, a list, or a list of lists here. And as you can see here, we have a 2x3 constant tensor. By default, since we use dot here, this is a float 32, and this is the content of it. If we created one with just a singular scalar, it would be of a single input or dimension. By default, it would be in 32, and the content would be 42. You can access different attributes of a tensor, so it's not just it's an object, right? So you can access its shape as well as data type attributes. So yeah, what are some operations we can, or how can we access these tensors? And this look will remind a little bit of NumPy here. So if you want to access all rows and from first column forward, similar syntax to NumPy. If we want to access just the second column, this means use as many, this is a Python notation, use as many double columns as you need it, and give me the second column. This is how you do it. And just some simple operations you can add to a tensor. You can square it. Again, the content is here. There is no, in NumPy, you have the .t, capital T operator here. That is actually a view, as it mentioned in the book, but here actually tf.transpose is the function you want to call. It will create a copy of your tensor and it will actually transpose it. And this operator in Python is the matrix multiplication, for those who haven't seen it before. The Keras backend is mentioned as well. I don't think it is used anywhere else. I think it's just as a side note that you can also, Keras has its own low-level functions as well. Cool. So what is the connection with NumPy, and how do I, if I have data in NumPy, how do I convert it to TensorFlow and vice versa? So let's start with a NumPy array here. How do I convert it to a TensorFlow? I can just pass it as an input to TF constant. That would be one way. And if I want to convert it back from TensorFlow tensor to a NumPy array, I just do it to NumPy. And then the different operations here. One thing that is important is TensorFlow is very picky with data types. So for example, if I have a tensor and of float type and of integer, you know, in most languages, one of them would be converted to the other one. For example, the int would be converted to a float. Here you actually get an exception that you cannot do this. You cannot add a float with an integer. You cannot add a float 32 with a float 64 either. By default, this is a float 32. So if you want to do any kind of operations, you actually need to cast them. You need to be very specific about the data type. So here, this is a float 32 by default. Here, I'm casting this constant from a float 64 to float 32, and now I can add. Strings, I think in the book it's mentioned that it uses the UDF-8 encoding, and there's a way for you to go from UDF-8 to Unicode and back and forth. We're not going to use a lot of string operations, as you can imagine, for our tensors. Then the chapter talks a little bit about sparse and ragged tensors, and that's a way for you to, or for TensorFlow to efficiently store large tensors. Think of it like large matrices that have lots of zero values. I'm not gonna go over them too deeply here. I'll just switch gears to variables. So far everything we've seen is constants, or operations are constants. One thing they need to keep in mind is that constants are immutable, meaning you cannot change them. You can do operations on them, but I'll create a new constant. What if you wanted to actually change the value of the data structure, right? So that means we need variables. And for that, TensorFlow has a tf.variable class and constructor. So this here, we're just passing a list of floats here. And if you wanted to assign anything to it, we can do it with the assign method instead of the equal method, or the equal operator. So if we wanted to double our values here, we'll just do 2x. So you see now the values are double. And if you wanted to access a specific cell in our tensor, the 0th row and the first column or the second column, and since we're 0 based index, we would do it like this. We can do item assignment like this. We actually have to use the assign function. and some other intricacies that are unique to TensorFlow here. Cool. The book doesn't cover tensor arrays, but they're mentioned in this notebook. It's good to be aware of them. Not not used a lot in this chapter though. So with that
Hey,
said,
George.
here, yep.
George, what is a tensor array? Because I think of a tensor itself already as an array. So
Yeah, in my opinion, yeah. I'm not 100% sure. Maybe the implementation in the backend is slightly different, but yeah, to me, a tensor is a multidimensional data structure, but on its own.
okay.
Maybe it has different methods, right? Maybe like here you can stack, you can do different like data set like or data structure like operations instead of just storing the data as it is.
Yeah, so like Chris said in the chat, maybe an array of tensors. So maybe it's more like a list or array of tensors. So you can do list-like operations on them, but it's probably not as fast for doing math on them the way you would do math like on a tensor, where you can just in one fell swoop say, add one
Right.
to every single number in the tensor.
Yeah, I haven't come across actually tensor arrays in any of our projects. Maybe, yeah, I'm curious what is the use case for them.
Yeah, I don't think I've seen that. Well, while I've got you paused, I thought I might just also add that, while TensorFlow does run on multiple things, you can run it on CPU, run it on GPU, TPU, whatever. The intent for creating TensorFlow was that it was going to run on GPUs. So it might seem a little weird, like when you said like, hey, you can't just do assignment. You can't just say, v equals 2 times v. You have to use that special assign function. But if you think about the fact that this is designed to run on GPUs, and GPU is a separate physical device from your CPU, so it has separate memory and it has these special math operations that it can do.
Mm-hmm.
It kind of makes more sense that you need special instructions for anything that you want it to do, and you can't do sort of the default things that you might normally do. And also because they're trying to optimize it, having special functions for say immutable tensors versus tensors that you're going to update, it allows it. I don't think that the math is any different when you double a constant versus you double a variable, but it allows it to optimize the computation graph to say, oh, I can do certain things because I know I don't need to worry about this thing ever being modified and stuff like that. So that's the kind of idea.
Yeah, absolutely. Yeah, you optimize it, but also you can cache it. So if that variable or computation is used multiple times, it just computed once and cached and reused.
Oh, that's a good point. Yeah.
Yeah.
In the chat, somebody asked what a TPU is, and so I think Google's the only company that's built TPUs. So they built their own special chips and boards, and they don't. A GPU, you can play video games, and it has other functionality on it for like stuff that you actually need for drawing graphics. But the TPU gets rid of all that, and it only includes the matrix multiplication and other stuff that you need to do neural nets. So no ray tracing on a TPU, for example.
Yeah, they're actually in version 3 or version 4, I think now. Yeah, so they've got a lot of evolution and a lot of improvement over time. And you can actually use TPUs now, even before on Google Colab or cloud computing. Awesome. Okay. So in theme with our customization, we're going to actually try first to create our custom loss function. We've seen different loss functions in the past based on the task we have, if this is a classification task or regression task. Here we're going to use, we're going to create our own custom function based on regression tasks. So we're going to work with the California housing data set from Scikit-Learn, and we'll create our own function, which means that we can calculate the loss between the real values and the predicted values, or any way we want. And this is how we're going to do this. So we're going to start with There's some libraries here, the data set itself, train test split, and the standard scaler for scaling our data. We're going to split it from this data set here and transform it. That's not really what we're looking for here. What we're looking for here is the actual custom function that we'll create. So this Huber loss is what we're going to create. And before I explain it, let me just give a visual here of what that looks like and why we're creating this. So the L2 norm, or the L2 distance function, as we've seen, like, or the square function between the error and the predicted values, penalizes heavily outliers. So that's one issue with it. On the other issue, on the other hand, the L1 norm, or the L1 error function, which is the absolute value of the predicted value minus the or the real value minus the predicted value, that one might make our training a little bit longer, and in few cases might not even converge. So it looks like we need something between L1 and L2 norm loss function. And that's the point of this Huber loss. If for lower values of error, Z is the error value, so target minus predicted value. For low error values, it behaves as a quadratic function. So it penalizes, say, large values close to 1 or -1. But for large values of errors, it actually behaves as the linear function. So you don't want a few outliers to increase your loss function so much that makes your training hard to converge. So in code, how do we do that? We're going to need only two things: the actual true labels, in this case y true, and the predicted values that our model generated, y pred. We're going to create the error, which is their difference, and then based on some threshold, in this case our threshold is 1. If we're between -1 and 1, so the absolute value of error is less than 1, we have what is called a small error. If that is the case, we're going to calculate the square error divided by 2. Otherwise, we're just going to do the absolute error minus the threshold here. This is just for how the Huber loss function is defined. And then this is a interesting statement. So this is basically an if condition. So TF where is an if condition in TensorFlow. It will look at our condition here, which compares the error less than 1. If that is true, we will return the square loss. We'll be in this quadratic region here. Otherwise, we're going to return the linear loss, this other region. We'll look at our training data. We'll build a very simple sequential network here with only 1 or 2 layers, one with 30 units. Activation, kernel initialization, those are not really important. The one that's important is in the compilation step. When you compile, the loss function now is actually the one that we defined above. So Huber FM here. So that's the only new piece of information in this flow. Optimizer, you can define any optimizer you want. This is meta metrics. You can plot whatever metrics you want. We're just plotting the mean average error here. We're not going to train it for too long, just 2 epochs, just to see the model that actually the loss drops, and you can see, you can monitor it for longer epochs if needed. So this is the only piece that is new in our tool set here. One thing that we can do is we can save this model. It will be saved on our local drive here. And also we can load it, and we can load it. The other thing that actually we're going to need is we need to, when we load a model that we've customized it, we need to tell TensorFlow where the function is. So the function is not actually stored as part of the model. That's why we need to point it back to the implementation of the function. So that's something to keep in mind. Now, once we load it again, we can just train it again just to make sure that it works. And as you can see, the loss keeps decreasing. So yeah, and one thing that the book mentions is right now we kind of hard-coded the threshold, but what if we wanted to have a specific or make that threshold a variable or use that as an input? What if we want a different threshold? And Aurélien just creates a function that returns a function. So basically a wrapper around our Huber function. This is exactly the same Huber function method that we saw, except that now the threshold is a variable that is passed by this wrapper function called create Huber. So what that allows us to do is we can call that method create Huber now with any threshold we want. So it could be -2, which is 2 or 3 or 4 based on our own experimentation. So one problem with that I kind of mentioned before is that the threshold, when you save the model, is not saved. What if we actually want to save the threshold as part of our model? So to do that, we actually have to use a very different implementation of this loss function. So this is the theme that you'll see in this chapter. So for quick prototyping things, you can build your own functions and play around with them, figure out which is the right value. But if you actually want to save all your hyperparameters, all your constants, or anything specific, you actually need to subclass. You need to extend an existing class based on what you're trying to customize. So if you're trying to customize a loss function, you need to extend keras.losses.loss. If you need to customize a metric, there's a keras metrics. You need to customize a model, you need to customize a layer, and so forth. You need to actually extend that class and basically extend that capability. Not only that, but you also need to tell TensorFlow what is the configuration now, and how do I map, and how do I recover any specific values. So using this getConfig method. So let's take a quicker look. So my new class now, it's not a method, it's a class now. It's called Huber loss. It's a subclass of keras losses.loss. There's an initialization constructor here that basically calls the parent method, but most importantly, creates a new attribute called threshold that we need when we call this. The next function we're going to need is call, which is actually the operation that takes place, and that is the calculation of the error function. How do we compare it to the threshold? If we are below that, we need the square value. If we're above that, we need the linear loss, and then the if statement that we saw above. And the last thing we're going to need is this getConfig, which apart from calling the parent getConfig, also maps the threshold name to the threshold attribute that is part of our model. And then the same, a very simple network here. There's 2 layers. There's nothing new here. The only new piece of information is right here, Huber loss, with 2 input. And now when we save it, when we recover it, you can see that we didn't have to specify the value is already there, the 2.0. And you can also see it from model loss threshold, that it's actually part of the model now saved. Cool.
There's a question about what the super in your code does.
Yes, so when you see anything that, anytime you see this super, this is object-oriented programming in Python. So you're extending, in this case, the syntax is I'm defining my class that extends keras losses.loss. So I'm inheriting all the methods, all the attributes that loss class has, plus I'm adding some of my own, in this case, threshold. So anytime that you see this super is for compatibility and for proper operation, we actually need to call the parent init method or the parent getConfig method, just so that all the attributes and all the methods of my parent class are also defined in the child class. So it's come from an object-oriented programming.
Yeah, so you've got that keras.losses.loss that you're inheriting, and then you're initializing all of the parameters inside of that with that super.init, and then you're passing in the keyword arguments.
Right.
So that's what that's doing. Yeah,
good question. Yeah. Cool. Okay, in the interest of time, what other customizations I can do? I can customize, I can build my own activation function for whatever reason, or I can build my own weight initialization function, right? Or I can build my own, how do I regularize my weights? How do I penalize large weights? Or if I have any constraints, what if I want my weights to be within a specific range? You can also do custom constraints as well. So just to build our own custom activation function, we're just defining a method here. This is the soft plus, so log of 1 plus e to the x. This is just another weight initialization technique, Glorot. You can define your own L1 based on maybe a customized version of it, maybe by modifying this factor here, as well as any constraints. So for whatever reason you want to keep only positive weights, similar to ReLU, you can check if they're negative, then return 0, otherwise return the weights. So in that sense, you can build a dense cell, which is one unit, with the custom activation function, which is here, a custom weight initialization function, which is here, a custom when during training, how do you penalize, or how do you take into account the values of the weights, as well as any constraints after gradient descent, any constraints that you need to apply to the weights themselves. Not sure how this will work, so don't take it and run into production. Cool. Yeah.
Hey, George.
Yep.
So if I could just add sort of like an editorial comment, basically what you're showing people is you can create regular Python functions, you can create regular Python classes as long as they're subclasses of the standard TensorFlow templates classes, right? And TensorFlow will figure out everything and all the things that you want it to do, the actual calculations, and we haven't talked about it, but all the back propagation, all of that stuff will work as long as you use only math functions that TensorFlow knows about. Right. So that's why you see like the square root and the absolute are the special TensorFlow versions of those, not standard Python or NumPy or whatever versions of those, right? Yep. That's the general gist here, right? Yep. I wanted to just add a comment. I don't know how things are because I don't write custom stuff very often. I don't know if you get an error or warning message, but like if you used NumPy square root instead of TensorFlow square root, you're either going to get an error message, or if you don't get an error message, it's actually even worse, because what that means is that TensorFlow will copy all of your data from the GPU back to the CPU, calculate a regular NumPy square root on it, copy it back to the GPU in order to obediently do what you told it to do. So I think in this case, it would be better to get an error message, but if you don't, then that's going to be a crazy slow operation because of the two copies.
Yeah, and I think this is mentioned in the exercise of the chapter. I think it will either get an exception or it will be painfully slow because of that trade-off that you mentioned of CPU to GPU.
Yeah.
And in addition, CPU works slower in several times than GPU.
Yeah, and the square root itself will be slower, but I would actually prefer to get an error message. So, but in case it's not clear when it says, oh, we're using TF square root and TF this and TF that, that's the reason, is because you don't want to copy the data. Again, assuming you're running it on a GPU, right? I mean, sometimes we prototype things on CPU. That's fine. I run stuff on my laptop, whatever. But when you're really running it, assuming you're running it on some other device that does very fast math, you don't want to copy things back to the CPU.
Yeah. Awesome. Then, yeah, this is just to make sure that our layer on our cell here works as expected. Just train it, make sure the loss drops down. And now when you load the model, we need to map any customization that we did, we need to map it back. We need to tell TensorFlow what is the actual implementation of those. So because if you see here, we just used functions. We didn't use any classes, right? So we need to tell TensorFlow that, oh, you just stored the name, but the actual implementation is defined above. This is the mapping of the name variable, and this is the actual implementation. And now we can actually reuse it after loading it. So this is the trade-off, right? If you use functions, you have to actually re-implement them every time you load the model. If you use subclassing, then the whole custom object or custom classes is stored for you. Yeah, this is just another note here that if you need any hyperparameters or constants to be stored, then you need to use subclassing. So in this case, regularizer is using init, call, and get config. One intricacy that I found interesting was for losses and layers, you need to implement the call method, but for regularizers, sorry, this is the syntax here. You need the underscore call method. So that's the only weirdness that I've seen so far. So if you are extending a loss function, a layer, or a model, you implement call. If you're extending a regularizer, initializer, or constraint, you extend or you implement underscore call. Yeah, nothing else here. Cool. So that was for loss functions. Similarly, you can do this for metrics. And the book talks a little bit about, what is the difference between the loss function and a metric function. So conceptually, they're the same. The one thing is that loss functions, they're used by gradient descent, so they need to be differentiable, at least where they're evaluated. So in the region that we need them to be evaluated, they need to be differentiable. And their gradients for convergent purposes should not be zero everywhere. They don't have to make a lot of sense to us, loss functions. On the other hand, metrics is something that should make perfect sense to humans. For example, accuracy. They must be easily interpretable, and they don't have to be differentiable or have zero grade or non-zero gradients everywhere. So they have to make sense to us, but they don't have to be these nice math objects that are needed for convergence. Having said that, you can use the same function or similar function both as a loss as well as a metric. So in this case, we are using the Huber function as a metric, which means that our loss is something else, mean squared error. So we are training our network using this loss, but just for printing and visualization purposes, that's all the metrics does. It has no impact on the weights or the way that the network is trained. It's just for pure visualization. How is that progressing over time? So we expect both the loss as well as the metric to converge to a value. And again, if this is a loss, it should go down. If the metric is similar to a loss value, it should go down as well. Cool.
George, is this notebook public? Is this something you could drop a link for us?
Yeah, so here,
it's in the, okay,
yeah,
okay, perfect.
Yeah. Cool. The other thing that, so speaking of metrics, the other thing that Aurélien talks about is this concept of streaming metrics, and the idea that if you calculate things as they come, so let's say you have a collection of data and you split it into batches, based on the metric that you have, it might make sense to calculate that metric on the entire data set or have a specific way to calculate it versus some kind of averaging based on different batches. And just to give you a very concrete example, let's say we have 8 predictions and sorry, 5 predictions, 4 of which were correct in the first batch. So that's 80% precision. In the second batch, let's say we got 3 positive predictions, but all of them were incorrect. So that's 0% precision. And if you do the average of 80 and 0, you're going to get 40%. But that's not actually the right way to calculate precision. So you should calculate how many true positives you have, which is 4 in the first batch, 0 in the second one, out of 8 total positive predictions, which is 8. So the actual precision is 50% and not 40. This is just to tell you that basically you need a way to keep track of metrics over batches and calculate them on your own. So Keras metrics precision does that for you, and this is an example here. The other thing is this is how do you actually implement it with the Huber laws that we saw. But again, this is now an extension of the metric, right? So Keras metrics metric, this is the only difference. We're subclassing it from metric. We're adding our own threshold, our own function, and we want to track how many total positives we had, as well as, or what is the total number of instances we've seen, and how many are right and how many we've seen. I think that's what this is. So yeah, how many we got right and how many we've seen overall. I'll skip this. This is very similar. This one too. Yeah, let's switch gears a little bit to layers, because these are more. I think you might have better chances of seeing this. As the book mentions, you can use the default layers that you have, but what if you came across a paper that uses an interesting layer or some kind of architecture that uses repetitive blocks? So when you hear that, it means, reusable code. So let's define things as layers. So if you want to build blocks with custom in a custom way, one way to do is you can use the Keras layers lambda class, and in here you would pass what does that layer do. In this case, it takes an input x, and it just returns e to the x. It exponents it. So I can give it a list, and it will take the exponent of each one of them and return me the result.
Microsoft is Google Chrome.
Sorry, say it again. Okay, there's any question, please let me know. So yeah, this custom layer can be used with the sequential API we've seen. We've also seen the functional API or the subclass API. You can also use it as an activation function as well. You can pass this exponential layer as an activation function as well, which is interesting. And one example use case of that would be if your regression model outputs a very large range from very small values to very large values, then you would use this exponent layer. So how do we use this in our network here? We have a sequential network. We have a dense layer, another dense layer, and we have our exponential layer here. We compile it, we fit it, we evaluate it. That's how we build it. If you paid any attention here, there is no state involved here. This is just an operation that takes place. It takes an input and it spits out an output. There's no state involved. There's no weight or bias involved. If we need state, that we need to subclass the keras.layers layer instead of keras.layers.lambda, right? So this is more like anonymous function, come from Python background. This is more of okay, let's build a proper class and maintain weights, bias, and all kinds of hyperparameters or values that we need. So we extend that. We call super to call the parent constructor. We need the number of units and the activation function for that layer. We build it with using this add weight method. So we need that for the weights as well as one for the bias, which each one of them has their own initializer. So the weights are using this global initialization. The bias is just zeros. And how many weights do we have based on the input? So the previous layer, how many connections are coming from the previous layer times how many units we have in our current layer. So this is a matrix basically. Then how do I actually use this layer? What does it do? It takes my input, it multiplies it, matrix multiplication with the kernel. This is the matrix I was telling you about, and adds a bias as a vector, and that will give me another vector. And a way to calculate now, I'll need to keep track of all the input shapes, and except for the last one will be substituted with how many units I have now. That will be my new output shape. And then just for persistence purposes, I need to also use getConfig to store how many units I have and what is my activation function. Notice here we use this serialization option for self.activation because just to make sure that this is properly stored as a H5 model. Then how do we use this? We have myDense as any other layer in a sequential model. For example, you have myDense, it has default values, or we can be very specific with it, number of units, what activation. Actually, those are the only two inputs that we can use, and the input shape. We compile it, we run it, and we can save it and load it because we implemented a class, we subclassed the Keras layers.layer. Cool. Just keeping an eye on the time as well here. The other thing that the chapter mentioned was multiple layers. So what if we have multiple inputs and multiple outputs? You can do that as well. You can subclass layer, and let's say you want to return two outputs. One is the sum, one is the multiplication of my inputs, and also need to return now a tuple for as shapes. So it's basically a multi-layer, multi-input, multi-output layer, more appropriate. Cool. I'm going to take a pause here for any questions. This notebook covers a little bit more content than the chapter, so I don't want to go too deep and take us too far from the book.
Yes, underneath of it, is TensorFlow static or dynamic?
Instance are flows. So
I can take that if you want, George.
yeah, go for it.
So my understanding, I never used TensorFlow 1, but TensorFlow 1 was static computation graphs. And now in TensorFlow 2, it allows for dynamic graphs. So when you saw the Huber loss, there's an if in there. It says, right, tf.where, if this value is less than 1, you're basically going to return, this squared thing. If it's greater than 1, you're going to return the linear thing. And that can only be determined at runtime. So it has to be dynamic. And my understanding is that you actually pay a little bit of price and performance. The TensorFlow 1 was faster with the static graphs because you can really do a lot of optimization against that graph. Whereas now, even if your model doesn't have anything dynamic like an if in it, it's still run as a dynamic graph, and it's not as heavily optimized as the static graphs were. But I saw something on performance analysis. This was PyTorch, but they basically work the same with their AutoGrad and everything. The backward pass does not have any ifs in it because it's always perfectly backwards of the forward pass. And so the backwards pass is normally heavily optimized. And so in fact, the backwards pass runs faster than the forwards pass. It's just like an interesting thing that I saw.
Okay, thanks. Because, you know, with all this
But I'm curious,
trouble,
what was the output that triggered the question? I didn't get that.
I asked if TensorFlow static or dynamic.
Oh, okay, got it. Okay, I thought you were referring to an output of the training step. Okay, got it.
Okay, and I have another question. Can you mutate something in place like we can in Python with TensorFlow, or it is not possible?
When you say mutate, you just mean change the value?
Yes, like for example, you want to change columns, you can do it in place. Column names, sorry, with Python.
Yeah, so George showed at the very beginning that a tensor, if it's a variable, you can overwrite it.
Yeah, assign. You just need to use assign.
Yes, I understand that you can overwrite it, but you always should assign it when you cannot mutate in place.
You can assign to a
To the
slice
old
of it.
variable.
You don't have to overwrite the whole thing. You can assign to any subset, like one column if you want to, if that's what you're asking, Maya.
No, this is not what I'm asking, for example, because in R, when we don't do anything changing in place, when you change a column, actually your whole, underneath of it, the whole data frame is changed and rewritten and assigned to the old variable.
Yeah, so Python and R do some great optimizations in order to reduce memory and copies. And so they use a data structure that has a level of indirection in it, so that like you can actually store data one way and you can view it another way. So I think George mentioned when you take the transpose of a NumPy array, it doesn't actually physically transpose it. It just updates the information as to how you should interpret the data to swap the meaning of rows and columns. Because
yes, I know this.
I know, but I'm just trying to get to. So
Okay.
GPUs today don't have that level of functionality. They're optimized for fast register access and math. And so it always uses the physical layout of the data. It does not use any indirection. So therefore, in TensorFlow, my understanding is that you can't do any types of non-copy optimization because it's always operating on a physical layout of the data. So when, like George showed, you do the transpose, a 2x3 has to be a 3x2. It has to allocate new memory to physically write the numbers in that row column order.
Oh, okay, thank you.
Yeah, good questions. The other thing is, what if we wanted to do something different for training purposes and something different for test purposes? So for example, dropouts or batch normalization layers, how do we use that? And the way to do that is by using the training argument in the call method when we extend the layer. So in this case, for example, we're having our own add Gaussian noise layer, which uses this standard deviation parameter. But the difference is that if we're in this call part, in this call method, if we're under training, we will create a Gaussian noise based on the shape of our input and add it to our input. Otherwise, if we're just doing inference, we can just it will just pass through this layer. And we use this as maybe as a first layer on our sequential model, just to add a little bit of regularization during training. Cool. The other thing is models. We can actually build custom models, and this comes as part of the code reusability. I'm gonna apologize here. I'm gonna switch from dark theme to white theme. This is this part that we're gonna build. So let's mention the chapter. We're gonna build a dense layer. There's a residual block which comprises of 2 dense layer with a skip connection. We're gonna use this 3 times, and another one, and then a regular dense layer. Going back to dark theme. So yeah, how we build that residual block? It extends a layer, the layers class. Then we will have a list for how many we need, and that's a parameter. It could be 3, 4, 5. It doesn't matter. So a for loop, just for us to create our own custom dense layers with a number of neurons, our own activation, our own kernel if we need. And then how do we do that skip connection? Our inputs is here. We will pass our inputs to this hidden layer that we calculated, and then in the end we will add them up using this skip connection. So we'll pass it through as many hidden layers as we needed. In this case, we just had 2. And then in the end, the output of those hidden layers will be added to the input, which is here. So we basically implemented surface switching again, this part here. So we pass it through dense, and this is a for loop. It could be as many dense as we need. And then in the end, we added it to the input. So that's just the block. Okay, now how do we use it as part of a model or a larger network? What do we need? The way that I think of this is, so extending model, this is the way to do it, is what ingredients do we need and what is the recipe to put those ingredients together. So the ingredients we're going to need is, apart from the super, is dense, a dense layer. We're going to need 2 blocks of our residual, not 1 but 2, as well as 1 for the output. So going back, sorry, we're going to need a dense, 2 of these, and 1 output. Then what is the recipe? How do we actually put them together? We take our inputs, we pass them through our first hidden layer, which is a regular dense, based on how many, this is a custom loop here, that how many times do I need to use my residual blocks, in this case 3. Then that output will be passed through another block, which is again another residual block, and that output will be passed to the final out layer, which is a dense layer. So that implements the image that we saw about a regular dense, 3 residuals, another residual, and a regular dense. So this is our custom model here. We create a model using that constructor. That one is the total number, the output dimension here. And we compile it with loss function optimizer, fit it, evaluate it. You can save it, load it, and all the great things that we've seen so far. Cool. So yeah, if you come across a paper that has its own residual blocks or its own custom blocks, you can implement them this way. Cool. Then the last couple of topics, quickly here, keeping also time in mind, is so far what we've seen is losses and metrics that are based on the output of our model, as well as the true values. But what if we want to do something a little bit more interesting or more complicated? Meaning, what if we want to take, based on our network, intermediate values, and we wanted to calculate a loss function there, or we wanted to print a metric there. So what if, for example, we wanted the output of each layer to contribute to the total loss? So let's say we have 3 layers. We don't want just the loss of the target value and our output to be impacting the loss, but we wanted the output of the first layer, the output of the second layer, the output of the third layer to impact our loss. How do we do that? And this is what is meant by this model internals. So this is a regressor, a custom model regressor that basically does 2 things. It outputs not only a regular output to a neural network, but also output something called reconstruction error, which basically is almost a way for us to keep an eye of the second to last layer. How close is it to the actual value? So basically, we want to keep an eye on this so that for large input values, we want to have maybe a large output value. If this is like, let's say, if the input and output are correlated. For a small input value, you want to have a small reconstruction error. So yeah, we define it regular hidden layer. We have our own dense, and we have a mean metric here, and the way that we would add to the loss is by this add loss attribute or method in the call function. So this is the new piece of information here. We're in addition to the actual loss function of the model, we're actually adding a weighted version of our reconstruction loss, and that is just the difference of an output, and you can place this output anywhere you want in the network, minus the inputs. It usually makes sense to put this really high in the network, like really close to the output. Okay, cool. So that was looking at the internals. Then the other thing that the book covers, again, keeping an eye on time, is we talked a little about this graph, and basically the book talks a little bit about automatic differentiation. So talks a little bit about analytic form, as well as how do you actually do this in code, given that you have limited resources, but as well as limited precision, right? And there's some very basic examples here of this is basically calculus in Python here. So two variable function f of variables w1, w2, and this is just like a heuristic of how do we calculate the gradient of this function with respect to w1. We just perturb it a little bit. We increase the value by a little epsilon here, 10 to the minus 6. We look at the difference in values. We divide it by that perturbation. What is the output? The output is 36. Again, this is the gradient of this function with respect to w1 at 0.5, 3 at this vector. Similarly, I can calculate the gradient with respect to this second variable. But how do you actually do this in TensorFlow? And this is where gradient tape comes into the picture. So in the backend, whatever TF operations we do, TensorFlow will build a graph, and we'll look at that graph in the slide. So that graph of operations clearly mentions what is the input, what are the different operations involved. Maybe I can share it now. So what is the input, if there's any while loops, if there's any if conditions, if there's any transformations, what are those and how are they related? The diff part comes when you want to calculate the derivative of the output with respect to any of the inputs or any other parameters. And the way to do that in TensorFlow is by using this, what is called gradient tape method or class, that basically says, keep an eye on this function z or function f, and calculate its derivative with respect to w1 or calculate its derivative with respect to w2. This is just some nuances. You can only calculate this once. So if you want to be able to, if you want to call the derivative or calculate it multiple times, you just need to pass the parameter persistent true. Otherwise, the gradient will be discarded at the end of tape.gradient for performance and storage reasons. Cool. So now we have a way to calculate gradients. What if we wanted to calculate gradients of constants? There's nothing changing there. So, or the gradient works only with variables, but what if we wanted to treat our constant as variables, if that makes any sense? So what if we basically wanted to see how perturbation on the input of our constants here impacts the output? To do that, we need to explicitly call this tape.watch, which means that, which tells TensorFlow to explicitly track what is the derivative of this function with respect to these parameters. And then you can get its gradients. This is just to describe how the gradient works, not that we need to implement or modify any of this. There's some more code here mentioning, first derivatives. In very rare cases, you might need to calculate derivative or derivative, which is called like a Hessian or second derivative of function. Again, this is just basically how do you do this in code? What is differential calculus, or not differential? What is calculus? How does that look like in TensorFlow? The other thing that the chapter mentions is this function decorator. And this is a way for you to create your own function here, but have TensorFlow do some kind of optimization, but also calculate it in a way that it can calculate gradients. Let's see, how do we use it here?
Hey, George, as like a high level thing, I know every now and then you want to calculate some metric and it's not in the predefined library. So you're like, oh, I got to write my own metric for this.
Mm-hmm.
And maybe you create custom layers. Doing custom stuff with gradients have you ever had to do that? It seems to me that's less common, that you usually just get to use the built-in stuff.
Yeah. You get the built-in stuff. The only thing I can think of is maybe using the gradients themselves as some kind of like loss or some kind of information.
So like if you were writing your optimizer, you might need to know the values of those gradients for momentum or for something like that.
Exactly. Yeah. That's the only reason. But modifying them, no.
Yeah.
Just
Okay.
more like yeah. Sorry. Then this is only in the notebook. It's not in the book, so I was trying to catch up here with the book. But this is how do you create your own training loop? I think this is what this talks about. So it has some utility functions of how do you pick a random batch from your input data set, and how do you display the status bar in terms of what is the current iteration, what is the total loss, what is the current step, or what is the total loss, what metrics, and so forth. And then so it is just for printing purposes. But yeah, this is what I wanted to get to. So with AutoDiff, right? With AutoDiff, you can actually go at the lower level and actually write your own training loop. So instead of calling model.fit, this is how you would implement it at the lower level, and this is how you'd customize it if you want to do something very specific at a epoch, batch, or if you want to treat your gradients differently, or if you want to modify them, or whatever you want to do. This is how you do your custom training loop. So there's two loops here. One is for how many epochs I have, let's say 5, and one another loop for each batch size. So 30. So based on my input divided by batch size is how many steps I'll have for the inner loop. I would pick a random input from my training set. I'll track gradients, meaning I'll pass my inputs to the model. I'll calculate what is the true label, what is my predicted value, what is the loss function. I will add that to the main loss function. And this is where I actually get to see or use the gradients. Tape-dot gradient of the loss function with respect to all the trainable variables. Not every variable in TensorFlow will be trainable. For example, like dropout or flat and don't have any trainable variables. Then the actual way to do the gradient descent step is using this optimizer apply gradients, using the gradients on the trainable variables. And this is how you actually update them using the assign method of, if you want to call it in place. Then print the loss, and then just some printing here, just so you can see this nice looking print function. This is just a fancier version of using TQDM, like tracking how the progress works. Cool. I know that we're running a lot out of time here, so the last thing maybe I can mention is let's see, maybe the graph itself. Yeah, and how do you make it dynamic? And the chapter talks a little bit about this, but there's a difference between, this is the main difference of TensorFlow 1 and TensorFlow 2. Like everything in TensorFlow 1 was running what is called in graph mode. And that's more like a symbolic operation of how the inputs are flowing through your network. And in TensorFlow 2, everything now is like what is called in eager execution mode. So the graph is not the central point of the structure. The tensor is actually the central point of the structure. So that's the main difference. These are content that are not mentioned in the book, so you know, feel free to skip them if needed. But yeah, I'll switch gears to the this last visualization here of if you have your own function, what does TensorFlow do in the back end of? So for example, you have a for loop in Python, it will actually create its own version of for loop, and it will try to optimize as much as possible so that if there are parts of this for loop that are independent, it can run them in parallel, just for optimization purposes. And if there's any node that will never be reached, it will probably prune it. And then this graph is actually what is stored and computed. And this graph can be now exported to other machines or other backends for you to run. I'll pause here. The autograph is a concept on its own. It has lots of material. I include a couple of links here on tracing and on autograph. Feel free to check them out. But in respect of time and respect of your other event, I'll pause here.
Thanks, George. This was definitely a dense chapter. A lot of complex stuff to get through. This was actually really helpful for me, George, you know, because I've learned PyTorch and I felt like, oh, I have more control with PyTorch if I need to do something that's sort of not vanilla Keras. But I'm realizing that there's things like the custom training loop and the custom layers that I really could have still used Keras and just done a couple of these things. Like there's one time, I can't remember, but I had images and I either wanted to go from 3 channels to 1, or I wanted to try and like insert some handcrafted features to like go to 4 channels. And I didn't know how to do that with Keras and TensorFlow. And so now I see I really could have just subclassed and created some special layer that went from 3 to 4 channels or whatever. And then I saw at the end of that, and it might have gone pretty fast for other people, but there's a function that you redefine, which is calculate the size of the output, you know, and so basically I would have just multiplied it by 4/3, you know, in order to get the new output size. And then all the other auto magic that Keras does, where the following layer knows, you know, how to map the inputs and the all that junk, right? All that would have magically happened. And so it's like, this is cool, like seeing that how, and I'm sure that Keras has come even farther since publication of the book. I don't know the details, but it's cool to actually see that if you get into a situation where you want to do something that's just a little unusual, wouldn't necessarily be that hard, and Aurélien provides some good examples that you can just basically copy paste and tweak a little bit of the innards. You've got all the pieces you need for it.
Yeah, it was interesting for me because again, I've only used the higher level APIs, so I haven't really got it down. I've used custom loss function and custom metrics, but I haven't used like you know, more advanced versions of that, or even like the gradient tape. It was interesting. Yeah. Do you see it every day? No. Is it good to know it's there? Yeah, absolutely. Specifically, if you want to implement something that's out there, that what Aurélien calls, you know, exotic, that has its own skip connections or your own architecture, you know, at least you have a way. It's just will take some time and effort to make sure it works right.
Yeah, I think there's some basic things that are built in, like if you want to just concatenate 2 inputs, but if they're like multi-dimensional, I don't know if concatenate works, you know, like if you have an image with multiple channels already, and for certain other things, yeah. I don't also want to write everything from scratch, but maybe I just have that one piece that's a little bit different because, you know, again, I've got something handcrafted that I'm just trying to like kind of sneak in there, you know, or maybe you've got a standard model and you think maybe if I add a second loss to it, I can help it learn the hard examples. You know, just some little tweak you're trying to make.
Yes, and in addition, you can do it with parameter and train the parameter together with the model, which is rather convenient as well.
To me, I like the visibility you get. Like you can actually stick out, you know, print out metric at each layer. Like if you really want to take a deeper dive, and for whatever reason, I'm just saying, right, and use that as a signal by itself. You know, that extra visibility of the network. Like that was interesting to me.
Yeah, I've definitely done some competitions, and it's sort of like, oh, I have this deep model, but I don't really know what is or isn't performing well, or you know,
Right.
it's hard to know what. There's some things out there, the whatever that is, Brian, what's it called? The layer scope thing for visualizing, like if you have images, visualizing like the different layers.
Like you're probing it, right? It's like,
Yeah, you know what I'm talking about, Ryan?
On
Red Cam?
TensorBoard? I've seen
No,
TensorBoard
it's
stuff,
just
but-
something, I can't remember what it's called, layer scope or something like that, for visualizing the activations on different layers.
There's the activation atlas, but there's also the more general technique. I'm blanking on the name too, though.
Yeah.
there's one called Grad Cam where you can see how the
Mhm.
gradient changes for different types of your
Yeah.
input.
Yeah.
Yeah.
That's right, GradCam. Yeah, that thing's really cool. One last thing I'll mention is I did read Appendix D, the thing on how the automatic gradients work.
Cool.
And it's really cool because, like, you know, if you learn calculus, you know that the gradient of x squared is 2x. But it's even cooler that you don't really need to know the closed form of something to just calculate the gradient at a particular point. So if you double some number and it's currently 5, then, you know, basically, you know, you multiply it by 2, the slope there is 2. And yeah, I thought it was pretty cool. It's not even a long chapter. It's only like 5-6 pages. Might take I think I did have to reread it, but
Yeah.
it's a
I didn't
cool,
read it. Yeah, I'll take a look.
yeah, it's cool that's included in the appendix. So I have a much better appreciation for like, oh wow, that's just clever. Again, you're not calculating everything closed form. You're just saying, for the numbers that I actually have, if I record that the value was 5 and I double it, then you can calculate what the derivatives are.
Awesome. Thank you, friends. Thank you for sticking with me.
Thanks, George. Any final questions for George on anything from this chapter?
You're welcome. I shared the link of my presentation. I have a PDF version on Slack, but I also have a live version on the chat here. Feel free to share it on the meetup page or other resources.
Yeah.
There's a link there with all the slides that are the links that I came across. Yep, you're welcome, friends.
Awesome. Great job, George. Thanks.
Thank you.
All right, so we are going to transition now. So on Saturday, we have 2 meetups. The first one tends to be topical, so either a lecture by someone, a professor, someone who, you know, has a paper, or the book club. And so then the second session is more free form. It's just where we have discussion of projects. People can ask data science questions, coding questions, project questions, whatever. So we're going to transition. So if you're not staying with us, feel free to drop at this point. And so then at this point, what we do is, I think Ryan might have some stuff to share about stuff that he's been doing at work lately, but it's just open. We'll open the floor to see first if anybody has question or would like to share about some project that they're currently working on.
Okay, I have a question, but it is not a project. It's a bit on site. We have now